So next up we have Dan Robinson from Paradigm, who's going to be talking about Plasma Stash.
Great. Hi, everyone. My name is Dan Robinson. I'm a research partner at Paradigm, but I'm here representing my own views. We're a crypto asset investment firm. So I'm going to talk about Plasma Cash. If you're not familiar with it, Plasma Cash is Plasma. It's an off-chain scaling solution on Ethereum. And what's particularly useful about it as a scaling solution is that it doesn't require data availability of these state transitions. So it shares that in common with state channels. And I'm going to be talking about how Starks actually are a really good fit for Plasma Cash and for fixing some of the problems with Plasma Cash, because there are these proofs that are part of it that I'll tell you all about. So Plasma is what's called a non-custodial sidechain. I think Patrick calls them commit chains. It's a sidechain that's committed to, say, the Ethereum main chain, and you can move assets onto and off of it, but it's operated by, say, one operator. And the key thing is the operator can't steal the funds and can't prevent you from withdrawing them. And withdrawing them can be done in constant steps, even if, no matter how many times the asset has been transferred. So these are the nice things about Plasma. There are some alternatives in terms of scaling that have different advantages and disadvantages. And one of the major ones that's relatively sort of adjacent to Plasma is rollups. So StarkDex, StarkPay, Stark Exchange, all the stuff that StarkWare has been working on generally falls in the rollup category, because that's something where it's similar to Plasma, except it requires that you guarantee data availability of these state transitions in some way, typically by just sort of splatting them onto the main chain in the call data. So that means that you no longer have this sort of infinite scalability where you can have as many state transitions as you want without any kind of scaling burden on the main chain. But you can get something like a 10x to 100x to 1000x advantage from this. So the big disadvantage that Plasma has compared to rollups is that it supports a much more limited set of applications, specifically really only sort of like payments and exchange. The one I'll be talking about today is just simple payments and transfers of non-fungible tokens, whereas rollups you could run whatever kind of computation you want. Anything you can verify in the EVM can be done with that. But I'm going to be talking about Plasma Cash here. So just to start, the core of Plasma Cash is based on this data structure called the sparse Merkle tree, or similar ones, an optimization of which I'll be talking about. So a sparse Merkle tree is a commitment. A normal Merkle tree is just a commitment to a list of values, and a sparse Merkle tree is a commitment to a mapping, to something where there's particular keys, and you can only open one key to one particular value. So here, most of this tree is empty, but the fourth key is some value v, and so it's very efficient to prove that slot 4 has value v, and you can only open this commitment to that one value. There's no way to prove that slot v is empty or anything else. And that's just sort of logarithmic in the total number of slots. So in this case, it's 4. Similarly, it's very efficient to do a non-inclusion proof. So you need to have these two primitives in order to support Plasma Cash. There's an optimization to sparse Merkle trees that's sort of the one that's currently used, which is a Merkle interval tree. And this one, it just allows this leaf here, this leaf at index 1, to cover a whole range, because all these values were empty, if you recall, in the sparse Merkle tree. So we just compress them all, and it just says this is the hash starting at 1, and then you just put you only have to actually put leaves when there's a value or one that isn't identical to its adjacent value. So it's a bit of a compression. So this means now our proofs are log m in just the number of non-empty slots in the Merkle tree. So that's just an efficiency improvement. Okay, so how do we use these commitments? So the structure of a Plasma chain is that it's divided into a set of coins. And a coin is some asset, and that asset is tracked by some particular slot in the Merkle tree, in the sparse Merkle tree, or Merkle interval tree. And the key thing here is that the coin doesn't move. The coin stays in the same place, and the owner comes to it and changes with each state transition in plasma. So if you're familiar with, on the Isle of Yap, this is some like monetary history 101. On the Isle of Yap, there are these rise stones, and these are used as money. And that's like, I don't know how big it is. It's very big. You can't. It's really convenient because it's very hard to steal this as money. But of course it's very hard to transfer it to somebody. So instead, when you transfer someone one of these, you don't actually have to move it. You don't give it to them. You just tell everybody, and there may be a public ceremony to this effect. That you just say that you're transferring one that everybody already knows that you own, and now everybody knows that someone owns the recipient owns it. So it's just like with these coins. Each of these right now is owned by some particular party. But then if Dave wants to transfer it, he just signs a transaction that, or if Alice wants to transfer something, she signs a transaction that sends it to Bob, and that transaction has to go in her slot, in the slot for the coin that she's transferring. So in this case, here it says slot 4, it could just slot 1. Alice just says, I'm sending this coin, and then that transaction is included at the right spot in the Merkle tree, and it actually just moves the asset. So so that's gave you a little preview of that. Transactions end up being Merkleized and put into one of these sparse Merkle trees or Merkle interval trees. And so each plasma block is just a commitment to, here are all the state transitions, here are all the coins that changed owners. And this is committed into the parent chain, and this is what allows plasma to prevent double spending. Because once it's been committed to the parent chain, there's just no way to for someone else to exit. And I'll describe how the exit game kind of protects you now that once you've been committed to the chain. So in order to exit, you can initiate an exit just by showing that at block 5 you provide an inclusion proof that says Bob owned this as of block 5, and block 5 is some block in the past. Now, what happens if somebody exits this from this outdated state, but Bob is actually already double spent it? Bob's already sent it to Charlie. In that case, you can just reveal this transaction here from Bob to Charlie, and that proves that this is an outdated exit, and that just cancels the exit right away. So Bob isn't able to double spend. Slightly more difficult to prevent is a malicious exit, and so the way that works is this can only happen if is an invalid exit. This can only happen if the operator is malicious, but what happens here is just Charlie never received this coin. Bob owns this coin. Bob thinks he owns this coin, but then the operator just says at this point Charlie owned this coin, and Bob knows that Charlie doesn't actually. So what Bob can do is just exit his coin, and the prior uncanceled exit wins. So whatever exit is earliest succeeds, and so Charlie's exit won't succeed because Charlie has no way of canceling Bob's exit. So this exit game basically works. I papered over a few sort of like subtleties that aren't really important for what I'm talking about here, but there's this problem, right? Which is when I get a coin, I need to know that no prior owner still owns that coin, or rather that I need to know that I can cancel any prior owner's claim on that coin. And in order to do that, I need to receive a proof that, say, here when Charlie receives this coin, we need to send Charlie a proof. The operator of the chain, or the prior owner, needs to show, look, here's your transaction at this particular. I received it this coin in block 3. It was deposited in block 3, and then it wasn't spent in any block since then. And then now you're receiving it. And so once Charlie sees all of this, Charlie knows that he owns the coin. So this history is independent of any other coin. This is only Charlie's Rise Stone that's actually being tracked by this particular slot, but it is linear in the length of the history and the number of blocks in the plasma chain's history. So that can be kind of a large proof. Fortunately, it's an off-chain proof, and this is what's really cool about Plasma Cache is that you have this proof, but it's only needs to be verified by the user, because on-chain it's verified by this interactive exit game. But when Charlie receives this coin, they're not able to take advantage of this on-chain interactive game because that wouldn't be scalable. So they actually just need to verify this proof off-chain, and that's where
the problem we're going to be solving with Starks, because these are big proofs. So like I mentioned, it's linear in the size of, in the number of blocks in the history, and it's also logarithmic in the depth of each of these proofs, because there's a non-inclusion proof or an inclusion proof for each of these sort of Merkle proofs. So if we want to support 1,000 transactions per second, and I think we know that we do, and we want to say no, we're not sacrificing any latency compared to the Ethereum chain. We're just going to have 5 blocks every minute and 12,000 transactions per block. That comes out to be about 2.6 gigabyte of proofs per year. And so I checked my iTunes library, and 2.6 is almost exactly the size of Pirates of the Caribbean: Dead Man's Chest, the second film in the Pirates of the Caribbean film, the Pirates of the Caribbean series. So this is a good way to remember it if you're familiar with my iTunes library. But generally, it's a pretty large file to have to send somebody 2.6 gigabytes every time you want to transfer them a coin. So remember, this doesn't go on chain. We're not lunatics, but you have to send this to somebody every time you transfer them a coin. Fortunately here, what we want are efficient. I was so undecided between Tony Stark and Arya Stark, and then Ellie used Tony this morning, and it was like a sign. So this we have a case here where we have these proofs, and it's a pretty simple proof, but it's really large, and we want it to be smaller. So this is a perfect use case for Starks. And what's cool is we're not going to verify any Starks on chain here. And in fact, there's nothing about this construction that needs to be built into the Plasma Cash contracts or anything. This is all just an upgrade that you sort of just layer on top of Plasma Cash, and it makes can make the proofs a hell of a lot more efficient. So looking at this, suppose an example, 1,000 transactions per second, 5 blocks a minute for 1 year. If you were just to give people the explicit Merkle proofs, that's 2.6 gigabytes. With Starks, it's only around 100 kilobytes to do a Stark. And thanks, Avihu, for helping with the benchmarks here and estimating these numbers. One downside of this is, so I checked, and 100 kilobytes is actually about the size of the screenshot I took for the lame iTunes joke that I had earlier. So that's much smaller. But now there's a downside here, which is it takes about if you were to just sort of do this on your laptop, it would take about 5 days in order to prove one of these. Just one of these. Now that might be okay. Because you're proving a whole year, so you only really have to do this like at the end of every year. You go, okay, I'm gonna do my Stark proof for the previous year, and you run your laptop for a couple days. This is also a very parallelizable process, so you could do this. You could have this run in the cloud and figure out how to generate this quickly, or the operator could run a service that generates these proofs for users. But if you want a slightly more efficient system, you can reduce the number of blocks, the frequency at which blocks are committed to the main chain. So you get these deeper blocks, but they're fewer than approved. And so for that, you'd still have an 80 megabyte Merkle proof per year, which is not a trivial amount to download in order to receive a transaction. But with Starks, you get the same space savings, but also it's a lot quicker. So one final optimization. It's a bit of a problem to have to prove the entire history of your chain. So if your coin, if that goes back a couple of years, it'd be really nice if we could just checkpoint the whole chain at some point, and you can do that off chain using Starks as well. So what could happen is the operator can just generate a proof of the current state of the chain and some information about the prior transactions that you need to cancel them, and just create a proof that this is the current state as of a particular point, and just provide that off chain to anybody who wants it. This is still a compact, like 100 to 200 kilobyte proof, but once the operator's generated this for this particular point, now all the other history proofs, all the coin specific proofs, can just start at the point that was checkpointed. So this takes a lot more. The proving time here is about linear in the number of transactions over that period, so 1,000 transactions per second. It turns out it takes about 10 seconds to prove every 1 second of history, so you're never going to catch up. But you could parallelize this and run this on a server, or you could just run something sort of that lags quite a bit behind, but still would be materially reducing the amount of sizes of these proofs. So Starks do also give us, I think, potentially some interesting ways to extend plasma cache and to make more complicated state machines viable in it. But I think that's going to have to wait for further work. So is building it, because I don't build stuff anymore that much. But I do make T-shirts. So if anybody builds plasma cache, plasma stash, I will make them a T-shirt. But it's something that, like, if you're building plasma cache, Georgios, I think you need to. This is just sort of like it's just a layer on top of it. This isn't something you even have to worry about in the base layer. It's pretty cool. The one thing is probably you should be using Pedersen hashes. So if you want to tell me about stuff you're working on, you want to ask more about this or my other work, you can reach me easiest at Dan Robinson on Twitter. All right, thanks everyone.
All right, does anyone have any questions?
Yeah, thanks. Do you mind to announce about this in plasma calls that we have? Because just recently on the last one, I talked about a similar approach. And the huge question is it possible to put proof for sparse Merkle tree inside the Starks? Did you try to do this somehow?
Yeah, I mean, so I've talked to. I haven't tried implementing this, but I talked to Avihu about it, and it's. I think it's a relatively straightforward process, especially I think if you use the Merkle interval tree rather than a sparse Merkle tree, it gets a lot more efficient.
Thank you.
Yeah. I'm sorry I haven't been on the plasma calls recently. I moved to the West Coast, so they're at 7 a.m. It's just a pain, but I'm sure they're great.
Yeah, but it's a great point just to continue because we're that's the point that we start to talk about this. Yeah.
Yeah.
Thank you.
Cool.
I had a question regarding I didn't quite get the negatives of the roll-ups, and so my experience is building roll-ups for like crypto collectibles, and the way that you've done your Merkle trees are very similar. I just didn't quite get the negatives of why a roll-up. I didn't quite get the negatives of that.
So with the roll-up, you have to put all the data for the state transitions on chain, right?
Yep.
So at least in theory, that gives you some limit to the scaling benefits, right? Like if you couldn't do 1 million transactions, you probably couldn't. You can maybe do 1,000 transactions per second. I'm not sure if you can with roll-ups on Ethereum today. That said, honestly, I think there's a good argument to be made that that's enough for now, and that's probably the. It's probably good enough and you get like a 100x maybe scaling benefit. So I think that's a pretty good argument. So yeah, I think plasma research is very helpful. For one thing, I think it informs some stuff about how to design rollups and to potentially make them more efficient. And because for sort of the eventual day when we want to kind of break free from the bounds of on-chain data availability.
Perfect. Thank you.